Hey everyone, and welcome back to another session from the Dr. Cool Cat team. Today, we're diving into a topic that, let's be honest, kind of freaks people out on the GED Science test: forces and motion. But here's the secret. It's not nearly as hard as it looks, and we're going to prove it to you today. Okay, so here's our game plan. First, we're going to take the panic out of the physics. Then, we'll introduce you to the big ideas, all the key players you need to know. After that, we'll put it all into practice with some real formulas and graphs. And finally, we'll wrap up with some final checks and common traps to watch out for on test day. Sound good? Let's do it.
All right, first things first, let's just take a deep breath. Because the secret to all of this GED physics stuff, the thing that makes it all click, is that it almost always comes down to just one single formula.
And this right here, this is it. This is your new best friend. F net equals m times a. That just means net force equals mass times acceleration. Seriously, this little equation is the master key that unlocks pretty much everything. If you can really get comfortable with this one idea, you are already way ahead of the game. So before we can start using that master key, we need to meet the main characters in this whole drama, the forces themselves. Let's get to know the cast, shall we? So let's start with the absolute basics. What even is a force? Well, it's just a push or a pull. That is literally it. Pushing a shopping cart, that's a force. Pulling a wagon, also a force. The only two things you have to remember are its size, which we measure in newtons, and, crucially, its direction. Okay, so what about this net force thing? Well, picture a game of tug-of-war, right? You've got forces pulling in both directions. The net force is the overall result. It's the winning pull that's left over after you cancel everything out. It's the force that actually gets things moving. And understanding this difference, this is a total light bulb moment. If the forces are balanced, like an even tug-of-war, they cancel out. The net force is zero, and the object's motion doesn't change at all. But if the forces are unbalanced, then you've got a winner. And that's what causes acceleration, speeding up, slowing down, or changing direction.
Now here is a classic mix-up we have to clear up right now. Mass versus weight. They are not the same thing. Mass is how much stuff you're made of. Your mass is the same whether you're on Earth or on the moon. Weight, on the other hand, is a force. It's the force of gravity pulling on all that stuff. So your weight totally changes depending on where you are.
You know, on the GED, you're pretty much going to see the same cast of characters over and over. You've got gravity, pulling things down, normal force, which is a surface pushing back, friction, which always fights against motion, tension from things like ropes, and an applied force, which is just your basic everyday push or pull. So how in the world do you keep all those forces straight when you're looking at a problem? You draw a free body diagram. It sounds fancy, but it's just a simple sketch. And you can remember how to do it with this acronym, FAST. First, find the context. Then add gravity. It's always there. Show the directions with arrows, and finally, tally them up. This little routine is a lifesaver, trust me. All right, we've met the characters, we've got our tools. Now for the fun part. Let's actually put these ideas to work and solve some problems just like the ones you'll see on the test. We're going to tackle both the formulas and the graphs.
Okay, let's try a classic example. Picture this. You've got a 4-kilogram box. Someone's pushing it to the right with 14 newtons of force, but at the same time, something is pushing it to the left with 6 newtons. The big question is, what's its acceleration?
Let's break it down. First, we need the net force, the overall winner. So, 14 to the right minus 6 to the left leaves us with a winning force of 8 newtons to the right. Easy enough. Now we bring out our secret weapon. F equals m times a. We just flip it around to solve for a. So acceleration is just the net force divided by the mass. That's 8 divided by 4, which gives us 2 meters per second squared. And don't forget, to the right, the direction is part of the answer. Okay, your turn to be the physicist. We've got a 3-kilogram cart. It's getting a 7-newton push to the right, but friction is fighting back with 2 newtons to the left. What's the acceleration? Go ahead and pause here, give it a shot, and then press play when you've got an answer. So, how'd it go? Let's check. The net force is 7 minus 2, which gives us 5 newtons to the right. Then, we take that 5 newtons and divide by the 3-kilogram mass, and you get about 1.67 meters per second squared to the right. Did you get that? Hey, drop your answer in the comments below. We'd love to see how you did. Okay, let's switch gears and talk about graphs, because you're definitely going to see them.
Now, there are two main types, and here's the one thing you absolutely have to burn into your brain. On a position time graph, the slope of the line is the velocity. But on a velocity time graph, the slope is the acceleration. Do not mix those two up. Let's zoom in on that velocity time graph because it's packed with info. It's simple, really. If the line is rising, you're speeding up, positive acceleration. If it's falling, you're slowing down, negative acceleration. And if it's perfectly flat and horizontal, that means zero acceleration, which just means you're moving at a constant speed. Oh, and here's a little bonus tip. The area under that line, that tells you the total distance you've traveled. Pretty cool, huh? Let's make that real quick. Say a graph shows the velocity going from 0 up to 8 meters per second, and it takes 4 seconds. Well, the acceleration is just the slope, the rise over the run. So that's 8 divided by 4, which is 2 meters per second squared. And the distance, that's the area of the triangle under the line. So 1/2 times the base of 4 times the height of 8, that gives you 16 meters. See? Once you know what to look for, it's not so scary. We are in the home stretch now. For our last section, let's talk pure strategy. Because knowing the science is one thing, but knowing how to beat the test is another. We're going to cover the most common mistakes and give you a checklist you can use on the big day. Okay, these right here, these are the classic traps, the easy points that people throw away. They see at rest and think no forces. Nope, it means balanced forces. They forget that the formula needs kilograms, not grams. They mix up what the slopes of the different graphs mean. And of course, they forget to include the direction. Don't let these simple mistakes get you. So to make sure you don't fall for those traps, here's a little routine. Just remember the word force. F. Figure out all the forces in the problem. O. Orient your directions. Pick which way is positive and which is negative. R. Reduce all those forces down to one single net force. C. Calculate using our favorite formula. And E. Evaluate. Take a second and ask yourself, does my answer actually make sense? And that's really what it all comes down to. You don't need to become a physics genius overnight. You just need a solid plan, a strategy for how you're going to attack these questions when you see them. And now you've got one. So I want you to take a second and really think about it. What was the one thing we talked about today that made it all click? Was it the tug of war idea, the force routine? That moment when it all comes together is huge. You just tackled one of the toughest parts of GED Science, so seriously, congratulations. We would genuinely love to hear about that aha moment in the comments below. Let us know what you got for that practice problem, or just tell us what concept finally started to make sense for you. If this guide helped you feel more confident, do us a favor and hit that like button. And be sure to subscribe for more no panic guides from the Dr. Cool Cat team. We'll see you in the next one.